So this is part of the magic of modular forms in some cases. That you have these finite dimensional spaces and different constructions of modular forms. They land in the same space. They give you linear relations, and it just to verify like two modular forms are equal, if they're in the same space and you know the dimension, you can find the basis. All you have to do is check enough of the initial coefficients are equal, roughly check the dimension number of coefficients are equal, basically. And once those are equal, automatically all the higher ones are equal. So to verify that two modular forms are equal, it's enough just to check some initial chunk of the coefficients agree, and then everything else is the same all the way up. All right. So of course, this is kind of the key detail. How do you prove that these spaces are finite dimensional? So we will get to that, if not today, then the next time. Though to impress upon you the usefulness of this, I want to give you an interesting application, more interesting than this weird identity that you would never have thought about if you didn't know about this stuff already. Like, well, that could give me some wacky identity between the sigma 3s and sigma 7s, but I didn't care about sigma 3s and sigma 7s. I just learned about them today, so big deal. So I want to show you a different application of the finite dimensionality of spaces of modular forms, and for that I need to introduce the modular form, the not quite modular form of weight 2. So it turns out when I said that these are all finite dimensional, maybe what I should have done was I could have come up here and said for M2 it's 0. There are no modular forms of weight 2 for SL2C besides the 0 function, and it's also 0. Whoops, I left off. In weight 0, the constants are modular forms of weight 0, and negative weight, there's nothing. In negative weight, they're nothing. And actually, the proof that this is finite dimensional kind of bootstraps by starting by proving this, and then using some special examples to kind of inductively get formulas for all the higher dimensions. All right? In fact, here, let me tell you what the answer is. It's nice to see the answer, even if you haven't yet seen the proof. So it's the greatest integer of k over 12, or the greatest integer. Oh, nah! Okay, I think I want to get k over 12 plus 1. And if k is 2 mod 12, it's this form. Like when k is 2, this is 0. And if k is not 2 mod 12, like for example, when k is 14, it doesn't work. So I made a mistake. What was that?
Wait, but 14 is 2 mod 12, so you wanted the top one.
Oh! Okay, everything is right. Yes. And when k is 12, then we start getting the 2. Yes. So this is for even k greater than 0. Okay, so we get a 4. So essentially it's k over 12. If something funny happens with k is 2 mod 12, you have to pay attention to, otherwise. Okay, so I'm not going to prove this right now. We will eventually get to this, but I want to kind of put this idea into practice. The idea of a modular form being a finite dimensional space, and to kind of show you a really interesting application of this. I want to take the Eisenstein series of weight 2, which, as the original double sum I mentioned last time, it doesn't converge absolutely. E2 of tau at double sum when the k is 2. It's not absolutely convergent, so it's really a delicate thing to try to make sense of. But when you write it like this actually makes perfectly good sense when k is 2. Okay? So let's use that. So we'll make a definition. I'm going to set E2 of tau to be this thing when k is 2. Now when k is 2, the numerator is minus 4, the denominator is 1/6, so you get minus 24. 1 minus 24, summing over all n, sigma 1 of n, q to the n, so this thing here is the sum of the divisors. Okay? That looks awful up there. Just know what sigma 1 is. The sum of the divisors to the first power. Okay? So again, the tau, q is e to the 2 pi on tau. That's where the tau is here. So this converges for all tau in the upper half plane. Or equivalently, this series, as a function of q, converges in the open unit disk. This holomorphic function, tau going to tau plus 1, it's unchanged. When tau goes to infinity, it's like q going to 0. You get the constant term is 1. So it fits all the conditions of being a modular form of weight 2, except I said that there's none of them. There's only 0. And this doesn't satisfy the transformation law for minus 1 over tau. So fact is that the value of this at minus 1 over tau, if it were honestly of weight 2, it would be this. But it isn't, and there actually is a correction term everywhere. So we have a systematic correction that accounts for the failure of this to be a modular form. In fact, these are never equal anywhere. The difference is always given by this expression. And so let's explore this function. It's not a modular form because, look at that, it kind of doesn't fit the condition. Nevertheless, it's useful. I'll tell you, given the formulas here, so I said before, this is holomorphic on H. It's invariant when tau goes to tau plus 1. And of course, as tau goes to I infinity, it goes to 1. So it's a nice well-defined value out at infinity. But it's not quite a modular because it has this extra funny term in the minus 1 over tau transformation rule. Now, there's another function that is invariant under tau goes to tau plus 1 and satisfies the same exact transformation rule. Namely for the imaginary part function, the reciprocal of the imaginary part function. So for points in the upper half plane, 1 over the imaginary part of minus 1 over tau turns out to equal tau squared times 1 over the imaginary part of tau minus 2I tau. Almost. I just need to turn the 2 into 6 over pi. So if I multiply this whole thing by 3 over pi, 3 over pi times the imaginary part has exactly the same rule as this. And if you replace tau by tau plus 1, of course you don't change the imaginary part. And so if you put both of these together, what you get is this modified function, e2 minus 3 over pi imaginary part. This linear combination still is invariant under tau goes to tau plus 1. Because both parts are invariant. And also, its value at minus 1 over tau is tau squared times its value at tau, because the extra funny term, by putting a 3 over pi in throughout here, when you subtract them off, this extra term disappears. And so, in fact, it exactly satisfies the modularity condition for weight 2 at tau plus at 1, 1, 0, 1, and at 0, minus 1, 1, 0. This function, e2 star, transforms exactly, it satisfies the modularity condition for weight 2 for all the matrices in SL2Z, because it works at the 2 generators. And when tau goes to infinity, this goes to 0, this goes to 1. Beautiful. So E2 star seems to be a modular form of weight 2. What's the problem? I said before, there's none of them. There's just 0. This is not the 0 function, by the way. What's the contradiction? Why is this combination not a modular form of weight 2. Look.
Is it not holomorphic?
It's not holomorphic. This is holomorphic, but the imaginary part function is not a holomorphic function. This is a real valued function. Non-constant functions are not, a holomorphic function can't take values in the real line only. Right? The open mapping theorem, the values are open sets. So unless it's a constant. Anyway, it's not holomorphic. And so this could be called a non-holomorphic modular form of weight 2. Okay, so there are more general concepts of modular forms. You might relax the analyticity condition. Okay, and so this could be considered a non-holomorphic modular form of weight 2. And so the E2 of tau, this is called a mock modular form of weight 2, or it's the holomorphic part of of a non-holomorphic modular form of weight 2. E2 is, maybe it's also called a quasi-modular form. So these things really are useful in other contexts. For example, there's going to be a talk later today by Steve Miller about applications of modular forms to sphere packing at high dimensions. And it turns out that this E2, the fact that it has this wacky transformation rule, but if you correct it by this, it has a clean transformation rule, it makes this a very useful function for certain purposes. And so I believe one of these functions, so this function is going to be showing up in his talk. So it turns out that just as I made this correction with the non-holomorphic function to kill off the extra term, you can make holomorphic corrections. Yes, what?
I think I figured out my issue. Never mind.
Is there a problem? No? Everything's fine? Okay. Yes. Sorry, if you have a question, you raise your hand and I don't notice you. You can just say, I have a question. Yeah. Okay. So, if we take, it turns out that just as E2 of tau has this funny transformation rule, so it turns out that, how do I want to say this here? So, also, the function 2 E2 of 2 tau satisfies, the same transfer. Well, you have to be careful. So this satisfies the nice rule for the two generators, and so E2 star actually satisfies the modularity condition for all of SL2Z. Now you can actually go backwards and figure out the transformation rule for E2 on any A tau plus B over C tau plus D. Right? Because you know it works nicely for this, and you can then put that back in and get it. And so it turns out, using that, it turns out that the difference, E2 of tau to E2 of 2 tau minus E2 of tau. This is an honestly holomorphic function. Right? This satisfies the modularity condition in weight 2 for all matrices in SL2Z where C is even. Okay, it does not satisfy the modularity condition in weight 2 if C is odd, for example, 0, -1, 1, 0. Oops. Okay, so remember, don't forget that the only reason we talk about like these two transformation rules is because 1, 1, 0, 1 and 0, -1, 1, 0 generate SL2Z. But you can have modular forms for subgroups of SL2Z. So there's an important family of subgroups, gamma sub 0 of n, written this way for historical reasons. It's the matrices in SL2Z that Well, have the lower left entry divisible by n. So when you reduce the matrix entries mod n, the lower left entry 0, concretely, you're saying the lower left guy is divisible by n. Okay? So it means for matrices in gamma 0 of 2, where the lower left entry is even, and this turns out to be, let me see, I think I worked out the, where is it? Right, so this group is generated by -1, 0, 0, -1, 1, 1, 0, 1, and 1, 2, 0, 1. Okay, so it doesn't have 2 generators, it has 3 generators there. Okay? So this is a modular form of weight 2 for a finite index subgroup. This gamma 0 of 2, this is a subgroup of SL2Z. It has index 3. And the, but to be a modular form for a subgroup, let me see, what does it mean to be a modular form for a subgroup? It should be holomorphic on the upper half plane. This is kind of the first example we're seeing of a function that's a modular form, not for all of SL2Z, but for a big subgroup of SL2Z. A modular form for, suppose I have a subgroup of SL2Z, say a finite index subgroup. So I'll make the definition and draw a picture, and then we'll be done for today. I want to come back, though, so this is going to have an interesting application to sums of 4 squares, as we'll see next time. But a modular form for a subgroup, what does it mean? So it should be, it's a function satisfying, it should be holomorphic, like before. It should satisfy, a modular form for a subgroup is of weight k. We need to have a weight. It's a function satisfying, it's holomorphic. It satisfies the weight k modularity condition for all A, B, C, D in that subgroup, not all of SL2Z. And then I need a third condition. Remember, for a modular form on all of SL2Z, the third condition is that the function is bounded as you go off to infinity. So the generalization of that, you notice in this case that f of tau is equal to 1 over this times that. Inside, for things in this group, subgroup, 1 over this times that is equal to f. But if the matrix is in SL2Z and not in here, these might not be equal. So the third condition is that 1 over c tau plus d to the k times f of a tau plus b over c tau plus d, this is bounded as tau goes to I infinity for all matrices in SL2Z. So if the group gamma is SL2Z, then these are equal for all the matrices, and so this is just another way of saying the original function. But in general, this third condition is for the full group SL2Z. The second condition, the modularity condition, is only for the subgroup gamma, and so this is saying something for a larger group. And so this condition is called being holomorphic at the cusps, and I want to draw a picture to indicate what that is referring to, and then that'll be it for today. So let me show you a picture. Fundamental domain for SL2Z. and a fundamental domain for that subgroup gamma 0 of 2, that index 3 subgroup. So if you go -1/2 to 1/2, and you take the point I, take the unit circle, and you go down and down to the line to 1/2, 1/2. So this is the this kind of funny looking region. The unit circle here, out to the 3rd and 6th roots of unity, and up vertically. So this is a fundamental domain for SL2Z. Every point in the upper half plane can be transformed by SL2Z into this region, uniquely, except there's some identifications at the boundaries. Apply tau to tau plus 1, this point goes to here. Fundamental domain for for gamma 0 of 2 is a subgroup, and so if you take the usual this fundamental domain for SL2Z, everything can be connected into here by SL2Z, but if I'm in a subgroup, I can't necessarily bring everything into here. But if I apply the matrix 0, -1, 1, 0, it takes this whole region and flips it over, and then if I take one more region, and this is STF, so you shift this over by 1, 1, 1, 0, 1, and then you apply S to that. So these 3 regions correspond to this having index 3. These 3, this is a fundamental domain. Every point in the upper half plane can be brought by a matrix in gamma 0, 2 into here. And notice what happens is at the point infinity, if you apply the matrix 0, -1, 1, 0 to it, goes to 0, right? Because you look at -1 over tau, as tau goes to infinity, it goes to 0. This whole region goes to here. And here you have, at the number 0, a curve that looks like, we call it a cusp. And so this is called a cusp from the shape. And so the third condition of being a modular form is related to the behavior of some function, roughly speaking, at this point. And so we call this third condition being analytic at the cusps. You don't see a cusp shape up at infinity, but you do if you transform it by SL2Z into any point on the real axis. Okay? And so next time I'll use these modular forms for a subgroup to prove the Jacobi 4-square theorem, and then we'll come back and prove the finite dimensionality. All right, that's it for today.